stop sharing. Okay, we're gonna get things started. Hopefully, Tara, you'll be able to fix the microphone. Maybe change the microphone setting, and that would work. But we'll still have a few minutes or so to get to it. So I want to welcome everyone to this session. It's the second CSAFM session. And for this session, we have 5 speakers. The first speaker, it's an invited, it's a guest speaker. And this session is understanding past, present, and future effect of climate on agriculture, forestry, and water resources. So the first speaker, Dr. Paul Bullock, will be speaking on climate and prairie crop production. He would give some historical and future perspective. So I'll turn it over to Dr. Bullock to get things started.
Okay, thank you. I'm going to share my screen here. Okay, and Zoom has decided to come up and give me something, which I don't want. Hang on, new share. There we go. Let's try that. Okay, is that working okay now?
It's working good.
Okay, should I leave my video on while I present?
If you can, if your bandwidth allows it, but if not, you can have it on.
Yeah, I'm at the university. I think there's enough bandwidth, but let me know if there's a problem with it, okay?
I will.
Okay, thank you. Okay, well, good afternoon, everyone. And thank you very much for this invitation to speak. I'm going to start just with a territorial announcement or acknowledgement, sorry, that I'm making this presentation from Winnipeg, Manitoba, which is Treaty 1 territory and the traditional homeland of the Métis Nation. So this particular topic is one that's been in my radar for over 30 years. I always thought that there was a little bit of courage required, you know, especially if you're going out to talk to farmers and the industry, the agriculture industry, about weather and climate and crops. You know, some people have some very strong feelings about that. Oh, just hang on. How come I try to get my, there we go, it's moving. So I know that you know, growing season weather is one of the critical factors that affects crop production around the world. Everybody knows that, and it can be a significant challenge for farmers in almost every year. Now, I have just come back from helping my brother and my father with seeding on the farm, and I can tell you that they sometimes have some very choice words to describe this topic I'm going to talk about. I'm going to keep this family friendly and just delete all of those kind of comments, but just mention that farmers often feel like they're in a battle with the weather as they go about their field operations. Canada is a very large country, as we know. In fact, we have the second largest area of all countries in the world. And despite the fact that less than 10% of Canada's land is arable, we have still an enormous acreage for cropping by global standards. And from this area, Canada now regularly exceeds 100 million metric tons of crop production annually. You can see this broken out by crop on this slide. The 2 largest are wheat and canola, but that total is made up of several different crops, and we have a good diversity in our crop production. You can also see the variability in Canada's annual crop production with year-to-year fluctuations of 10 to 20 million tons being common over the past 30 years. And there's several factors that cause this fluctuation. But an important reason is the dominance of prairie production in this total. So this is the same slide, but now it's just showing the total, combined total from Manitoba, Saskatchewan, and Alberta. And that's 75 to 80% of Canada's total crop production. The prairies have a comparatively small proportion of grain, corn, and soybean because those crops are predominantly grown in Eastern Canada, but the production of all the others occurs mainly on the prairies. And we can see that those fluctuations in Canada's annual crop production originate mainly from the same fluctuations that occur in the prairies. The most prominent production declines in this time series I'm showing occurred in 2002 and 2021. And both of those years were strongly impacted by drought, as well as dry conditions that preceded the drought year. And this is something that we need to expect because, of course, the prairie climate is semi-arid to subhumid. So drought is an inherent feature of the climate. And in some years, it's just very severe. In my early career in the 1990s, I was monitoring world grain production for the Canadian Wheat Board. And this included monitoring crop yield potential on the prairies. And there was a huge focus on the impacts of drought on crop yield. And you can see why this was the case in this figure. The big droughts, quote unquote, were clearly, 61, 1988, 2002, 2021. And, that's where we had very big shortfalls. And this was a big deal at the Canadian Wheat Board. Now, you can also see that the crop yield that was achieved, in this case for spring wheat, prairie spring wheat, during those droughts has increased over time. So we're seeing, higher yielding varieties, improved crop production, higher crop input levels. And the other factor that is often overlooked is the fact that, we've seen the carbon dioxide levels in the atmosphere rise 100 parts per million over that same time period. So, these crops and in fact, all plants in the world have been consuming an increasingly enriched diet of atmospheric CO2. And that also helps in terms of increasing crop yields. So there's many different factors that do affect crops, but climate is obviously one that plays a very important role. So first, let's just look at this importance of these growing season moisture deficits on prairie crop production. So this is a map. It's showing growing season precipitation in 2021 from April 1st to July 31st. It's a percentage from the normal. And you can see that these precipitation levels were below average for most of the prairies. Some areas had very significant shortfalls. And in 2021, prairie crop production was down 40 to 50% from recent years. Now, if we contrast that with exactly the same thing, but in the same time period for 2013, this is April 1st to July 31st, 2013, the rainfall totals in this case were all average to above average. And this is something that's ideal in a semi-arid climate like the prairies. The yields that year were exceptional. So when you contrast this to 2021, you can see how favorable growing season precipitation is really quite important for crop production in Western Canada. So if we go back a little bit further, this is 2002, and that was also a year with greatly reduced crop production. So the map on the left shows the modeled mean root zone soil moisture in July 2002. And of course, this is obviously a function of the growing season precipitation up to that point in time. And you can see that in Alberta and in Western Saskatchewan, there are some very low values, and that's not positive for agricultural crops. It would be near the peak of their growth phase to have such deficient soil moisture. The map on the right illustrates the crop yields reported that same year. And you can see that there's a very definite link between that deficient soil moisture at the peak of the growing season and the crop yield. I dug down into my archive of old files and found this slide. This goes back from one of my presentations during the Wheat Board days. So back then, in the 90s, mapping software was still a little bit in the early phase of development. And this was considered a pretty high-tech map at the time. Although it's crude by today's standards. The purpose is, again, to illustrate the extent of the growing season rainfall in 1988, showing it again as a percentage of normal. This is for April, May, June. And this was another year when prairie crop yields were severely reduced by the drought. And this slide comes from the same presentation as the slide I just showed you. And it was one that I used to use when I was at the Wheat Board to emphasize that correlation that we see between prairie crop yield and growing season precipitation. So this is, in this case, it's Canada Western red spring wheat yields. They've been detrended, and the May to August rainfall total is shown alongside. It's not a perfect correlation by any means, but it's strong enough to kind of make the point about that link. Dr. Graham Walker was Director of Weather and Crop Surveillance at the Wheat Board until 1991. He developed a model for wheat yield estimation on the prairie and published it in 1989. The model was basically a method for determining a precipitation deficit based on water supply minus crop water demand. He termed that a drought index. Now, up to this point in time, I've been talking about growing season precipitation, and you might say, well, what about the antecedent soil moisture? Does that not have an impact? And the answer is yes, it does have an impact. And in this figure, this is from Graham's paper, I'm trying to illustrate that. The supply of water, this model reached all the way back to the previous fall. And even though it gave a somewhat lower weighting to the value of that moisture ahead of the growing season, it nonetheless played an important role. So he accumulated over an entire 12-month period, and then calculated the evaporative demand during the growing season. And so the drought index was based on that supply of precipitation versus the demand. And the more that the demand exceeded the supply, the greater was the effect of the moisture deficit. So what the model did that he created was to calculate this drought index for every weather station on the prairies, and then weight the value for that weather station according to the acreage of wheat historically grown in that vicinity. Once that weighted drought index value was calculated, the model was then used like a simple linear regression between the historic drought index values and prairie wheat yields to come up with a way to convert the index to a yield estimate. Now, since at the time that this was developed and utilized, the moisture deficits that we were seeing on the prairies was really the key limiting factor for crop yields, this model was amazingly accurate. It was an absolute huge asset to the Canadian Wheat Board. The Wheat Board had jurisdiction over the sale of all wheat in Canada. So knowing the total production in any given year was a very strategically important information. However, even by the early 1990s, some of the limitations in Graham's model were becoming apparent. And you can see that on this slide, what happened in 1993, for example. The problems in 1993 actually originated 2 years earlier and half a world away. In June 1991, Mount Pinatubo in the Philippines had this massive eruption, and it was the second largest volcanic eruption that actually occurred in the 20th century. The sulfur dioxide that was pushed into the Earth's atmosphere reduced solar radiation levels, the incoming solar radiation, for the next 2 years, as you can see in this particular figure. Global mean temperatures were reduced by approximately 1 degree Celsius in 1992. Now, this temperature anomaly was not evenly distributed around the globe. And I know this map is not easy to see, but I'm highlighting the central portion of North America. So this is showing June, July, August 1992 temperature anomaly, and it was 2 to 3 degrees colder than normal. For the prairies, where you're near the northern limit of crop production, this was absolutely devastating, because by July of 1992, we could already detect late development of the wheat crop. We had alerted the sales department that there was very high likelihood of severe frost damage to the crop, even if the fall frosts occurred near their long-term normal dates. But what happened was the frost came earlier. By the third week in August of 1992, almost 3/4 of the prairies had received at least one, and in some cases, multiple hard frosts. Wheat quality in 92 was very poor because of the frost damage on immature wheat plants. So what happened in 1993? Okay, so the information in this slide comes from the US, but it was kind of the best overview I was able to put together. The southern prairies, of course, border the northern plains of the USA. And this map shows the departure from the normal precipitation from June through August 93. The values in the northern tier of the US are somewhere between 4 to 12 inches of rainfall above the normal. And this was the same situation that we saw in the prairies. The growing season was cooler than normal, yes, but it was also much wetter than normal. And it was little wonder that Graham's model did a poor job estimating the prairie wheat yields in 93, because excess moisture is obviously a limitation to crop yield, but a drought index model really doesn't reflect that factor. Anyway, despite the lessons that we should have learned about non-drought factors that can impact crop yields, drought continued to be a very key research focus. And in the early 2000s, we had extensive and successive drought years, and they appeared to vindicate the viewpoint that drought was really important. So in 2005, following all these drought damaged yields, we started a large multi-institutional research program called the Drought Research Initiative. It officially started up with 5 years of funding from the Canadian Foundation for Climate and Atmospheric Sciences in July 2005. The timing was awful, okay? I don't know, does anybody remember what Manitoba looked like in July 2005? Just a little reminder here, this was the Red River Valley that flooded, and it was very unusual. Normally these kind of floods were occurring at the time of spring snowmelt. This was a result of heavy late June rainfall, which was very unusual. It gave way to some very interesting pastimes that you normally don't see in July in Western Canada, but this facilitated a few things that were a little bit different. When we started the Drought Research Initiative in July 2005, we didn't know what was coming. Year after year, while we studied drought, the concern shifted away from that and focused on excess water and flooding, okay? And it's not surprising. Farmers had much different concerns than drought. This photo is courtesy of Scott Day. It's kind of an illustration of what he would term the awful spring of 2011, struggles with seeding the crop that year. And note, this is north of Waskata in what is the quote, dry southwest corner of Manitoba, which certainly doesn't look very dry. And it wasn't just there. You know, this is another photo from that same year. This is from central Saskatchewan. So it was a widespread problem. Excess water was really the focus. Nobody was too interested in drought anymore. With time, it became apparent that 2005 actually marked the end of a dry cycle that had lasted almost 3 decades. Now, this is a slide that was put together by Les Henry at the University of Saskatchewan. It's showing the observation well records from the Goodale farm near Saskatoon. And what you can see is that after declining kind of steadily, more or less from the 1970s to 2005, the water level climbed rapidly after that point in time. By 2010, it exceeded anything in the previous record. It wasn't just one fluke at one location. The pattern was widespread. You can see the same water level trend in this record from the Melfort observation well, and you can find it in several others as well. So we definitely changed it right at 2005 from drought to excess water. The shift in the moisture regime on the prairies also shifted the types of insured crop losses. I'm trying to illustrate it here using examples from the Manitoba Crop Insurance Corporation annual reports. Over the long term, from the mid-1960s up to 2003-04, the 2 largest sources of insured crop losses in Manitoba were equally split. You can see there's drought and heat, and there's excess moisture. And then the rest, the remainder is made up from everything else. What happened, though, is that if you just move this forward a few years, now the largest insured loss is excess moisture. So you can see the impact that that series of years had, not only because of the moisture regime, but on the types of insured crop losses that were occurring. If you look beyond the general trends, there's a more, I think, insidious concern for prairie crop production. And in this slide, I'm using the 2011-12 annual report, again, from Manitoba Crop Insurance, to illustrate what I think is an important point. In the 2011 growing season, the largest cause of insured loss for the crop insurance program was excess moisture. And that's not surprising considering the photos I just showed you from 2011 earlier. In fact, Manitoba had a record number of insured unseeded acres in 2011. And it ended up with the largest insurance payout for that loss in its history. But look more closely at that pie chart. There was also a substantial payout made in 2011 for crop losses due to drought and heat. So you have two completely opposite moisture extremes occurring within the same crop year. So there were Manitoba producers who received insurance payments for unseeded acres due to excess water, and also payments for yield losses due to drought in that same year. So we're seeing these shifts from excess water to drought that can happen within the same year, as well as interannual shifts from drought to excess water and back again. And this type of variability is extremely difficult to manage. The most appropriate crop and fertilizer strategy during a year with excess water is completely different than that for a drought. But if you don't know what's coming, and it could change perhaps even halfway through the growing season, how is it possible to optimize your crop productivity? I don't have the answer. This is a very severe challenge. And it's actually happening right now as we speak. The 2021 growing season on the prairies was severely drought affected. Many municipalities declared a state of disaster, as shown on this particular slide. The drought was especially severe in the Interlake and the central regions of Manitoba. But you can see by this map from the Canadian Drought Monitor, it was a significant factor across much of the prairies in 2021. We shift ahead to 2022. Many of those same areas that were drought affected the previous year are now dealing right now with excess water and flooded conditions. There's going to be significant areas that are not seeded in 2022 as a result of excess water. And many of the fields that do get seeded will probably have reduced crop yields as a result of that late seeding. The start of 2022, the most severely drought affected areas are in southern Alberta and southwestern Saskatchewan. So you can see the nature of this variability. How do farmers increase their resilience to this highly unpredictable and changing extremes in weather conditions? A recent analysis of dry spells in Canada reveals that in the Prairie region from 1979 to 2018, there were areas that experienced both positive and negative trends in the number, in the total duration, and the maximum dry spell duration. So a dry spell here is defined as 7 consecutive days with precip less than 1 millimeter. So a dry spell isn't an agricultural drought, but it's certainly an indicator of the tendencies for consistent lack of precipitation. And some are seeing a significant positive trend in those, and some are seeing a significant negative trend. And in the same study, it appears that there is a somewhat stronger positive trend for the number and duration of wet spells over that same time period. And if you look closely, there's areas on the prairies that have experienced increasing numbers and duration of both wet and dry spells. So it's very clear that farmers are having to deal with this increasing variability of moisture. This is translated into increasing variability of crop yields as well. So this figure is showing the provincial yields of wheat in each province individually and for 3 consecutive decades. And what you can see is that the mean yields in every province are increasing over time. So well done to the ag industry for that particular trend. However, if you look at the standard deviation, it's also increasing. And even the CV, to some degree, in Saskatchewan and Alberta, the rate of increase in standard deviation is outpacing the increase in the mean yield. It's not just for wheat. This is the exact same slide, but using canola yields this time. Again, you see the rising mean yield of canola by province, by decade, but that same pattern with higher standard deviation in CV is also apparent. So there is definitely a greater variability that's affecting our yields. So what about future climate effects on prairie crops? So this is an example from one study. It covers the crop area of Alberta, Saskatchewan, and a bit of Manitoba. The maps are showing the projected change in dry days, which is on the left. And these are days with less than 2 millimeters of precip. And it's also showing the projected change in precipitation deficit, which is the map on the right. In both cases, there's a projected increase, in other words, becoming drier, okay? So the increase is statistically significant in those areas with the black dots that are shown. And it's a very sobering projection. It would certainly indicate we should be expecting increased impacts of drought. However, I think it's very important to note the climate change scenario that formed the basis for this projection, okay? So this is the RCP85, and that representative concentration pathway is quote unquote business as usual. No major progress towards mitigation of greenhouse gas emissions and extensive climate change. So this would be a worst case scenario, and perhaps with some greenhouse gas mitigation before this time period, these increases in dry conditions may not be as large. The context for the future prospects of climate change is very, very important, okay? So in this study, it's the standardized precipitation evapotranspiration index that's being used to assess changes for wetter or drier conditions across Canada. This study used 3 different RCP scenarios, ranging from across the top, an aggressive greenhouse gas reduction and low climate change, an intermediate one in the middle, and then on the bottom is again that RCP85, which is extensive climate change. It also shows 3 different future time periods starting in the next decade and extending to the last decade of the 21st century. And the study shown on the previous page used that RCP scenario with the most extensive climate change, and it looked at the time period at the end of the century. So that study would be comparable to the map on this slide on the lower right. And you can see that if you look at something more recent, like the next decade, under a situation where you have more aggressive greenhouse gas reduction, you get a fairly different outcome. So the point of this is that these are still unknowns. These are particular scenarios that can be used to model future climate change, and you can get some fairly significant differences in outcomes depending on what time period you're looking at and what RCP scenario that you actually use to do the projection. So I'm going to summarize. I don't have a lot of answers to these questions. I'm just raising what I think are some very significant concerns going forward for crop production in Western Canada. And if we put this into some context now, Canada's crop production originates mainly from the prairies. So these climate effects on prairies crop production have a significant impact on the production in the entire country. Severe droughts have been and continue to be the main cause of major prairie crop yield loss. The yields during the droughts have increased over time. Other weather factors are also important for crop production, including excessively wet growing seasons and of course early fall frosts. So drought is not the only factor that should be looked at, but it's often one of the most severe. Both growing season moisture conditions and prairie crop yields are becoming more variable over time. This will be a challenge for crop insurance. You're looking at more frequent payouts being required over greater acreages because of this variability. Future climate impacts on moisture conditions and prairie crop production will depend on the degree of climate change. And depending what you assume that change will be, can have a very large effect on what your outcomes will be in terms of these extreme values. Prospects for increasing weather variability is going to cause challenges for prairie crop production adaptation to climate change. It's just very difficult to adapt to something that is so variable and so unpredictable. So I'm going to close. I just want to make acknowledgements, and this goes out to just scores of people, all of my academic supervisors, grad students, postdocs, research associates, funders, colleagues. You know, I've worked with many different people over the past 40 years, and the work and analysis and insights provided have just been so valuable. I've really been fortunate to have a lifelong learning experience with all of my colleagues, and all of you have contributed significantly to this presentation. Thank you.
Thank you very much, Dr. Bullock, for that wonderful presentation. I think we can squeeze in just one quick question and maybe a very brief answer if that's possible. So I have a question here from Catherine. Great talk, Paul. To what extent do you think changes in pest management practices and seed genetics would help mitigate this type of variable risk going forward?
Crop management practice, and was it seed genetics? Was that the other?
And seed genetics, yeah.
Yeah, and I think there's already been some of that has occurred. That's a good question. You know, just driving back through Saskatchewan, Manitoba, you can see how the seeding, how much it's changed since I was a farmer 40 years ago. With you know, direct seeding, there's more residue, and it's helping to increase the health and resilience of our soils. And I think it buffers the impact of drought to some extent by retaining soil moisture. Again, we've seen the impacts of seed genetics. I think part of those increases in yields that we're seeing in the droughts can be attributed to improvements in seed genetics. So that will help to mitigate. What it does for dealing with dry and wet conditions, I'm not sure, other than hopefully just to maybe dampen that fluctuation a little bit.
Okay, great, thank you very much. I'll try to move things ahead. Thank you so much. I appreciate you accepting our invitation to come and give this guest talk. Thank you very much once again, Dr. Bullock. And I would move to the next speaker, Dr. Menasan Kabela, and he would be speaking on the effect of delayed harvest date on gluten strength of Canada Western Red Spring wheat. So please take it over, Menasa.
Thank you, Rotimi. Let me just share my screen here. Share. Okay. Can you see my screen?
Yep, it's showing up good.
Okay, thank you very much. I just want to start by acknowledging that we live and work on the original lands of the Anishinaabe, Cree, Dakota, and Dane peoples, and on the homeland of the Métis Nation. My talk today is going to be on wheat gluten strength. This research that I'm going to be presenting today was actually part of a bigger study that had 6 subcomponents. And the whole study emanated from the fact that around 2012, there was a big outcry about the fact that Canada's wheat seems to be having some problems with gluten strength. Remember that Canada's wheat was the golden standard when it came to the quality of the wheat. So this bigger study then was initiated to try and find out what was the problem that is causing these concerns about gluten strength. And one of the studies that were done is this one, which I'm reporting on now, right now. One of the most important factors that affect wheat quality in Western Canada is actually the timing of harvest. That means, when do you harvest? In some years, harvest date may be delayed, mainly due to the weather conditions. It could be raining, it could be snowing. While the ideal moisture content for wheat that is being harvested should be around 13 to 15%. In cases when harvest is delayed, then there can be substantial losses in terms of yield, and also the grade and the grain quality, and finally the income as well, because the grading, if your grain is downgraded, then you are going to get less money from that grain. In most cases, the losses are due to lodging, shattering, pre-harvest sprout damage, and frost damage. It's also important to emphasize that harvesting wheat with moisture content that is less than 20% leads to higher likelihood of the grain being damaged. And of course, if you harvest wheat that is high in moisture content, you have to dry it to reduce the chances of spoilage. Now, these are just snippets from some papers, which some were in 2018, some in 2016, where everyone was crying out, more fall snow makes tough Alberta harvest season tougher. It's depressing, it's stressful. Harvest delayed by rain and snow in Southeast. Cool, rainy weather conditions lead to catastrophic harvest for Manitoba farmers, producer group says. So these things happen everywhere in the prairie. So what was the objective of this study? The objective was to investigate the effects of delayed harvest on the wheat quality and gluten strength of 4 leading varieties of Canada Western Red Spring wheat grown in Western Canada, recognizing that there has been a lot of work that has been done to try and understand the effect of delayed harvest on grain quality. However, nothing much has been done to try and understand the effects on gluten strength. So why gluten strength? You might ask yourself that question and say, why are we concerned about gluten strength? The concern is that wheat gluten strength is a very important factor when it comes to baking bread. It contributes to the ability of the dough to rise and maintain its shape when you're baking it. That's called elasticity and extensibility. The quality of the gluten actually determines the baking quality. So that's why it's so important to understand gluten strength. Gluten proteins, of course, account for about 75 to 85% of the total protein in bread wheat. So the problem is that variations in gluten strength present challenges to both the milling and baking industries, because it becomes difficult to maintain a stable quality. And you have to be adjusting the baking process to compensate for the fluctuations. Now, if you look at this picture here, it shows 2 bread, one which has been baked with a weaker gluten strength, and the other one with a stronger gluten strength. The one that stays stronger is the ideal one. Now, materials and methods. How did we do this study? I have to come up upfront that unfortunately we only had 1 season for this study, but we had 4 locations in Manitoba: Cross Isle, Kelvin Farm, Carberry, and Brandon. And then we had 4 spring wheat cultivars, and we grew those ones at each site. The varieties were Glen, Carberry, Brandon, and harvest. We used a randomized complete block design, and we utilized 4 harvest dates. The first harvest was at physiological maturity, which is about 15 to 30% grain moisture. And then the second harvest was 2 weeks after harvest 1, when the grain moisture content was about 13 to 15%. This is when most of the producers would be harvesting. And then harvest 3 was 4 weeks after harvest 1. And again, harvest 4 was 6 weeks after harvest 1. We took some grain samples, kept them in a drying room until they were processed. This map here just shows the sites where the experiments were done. This is Cross Isle, Kelben, Carberry, and Brandon. So we took some grain subsamples and we sent them to a lab here in Winnipeg for cleaning and grading. And they looked at grading factors that they measured were moisture content, test weight, FDK, EGOT, midge, and sprouting. And then we did some flower quality analysis here at the University of Manitoba following approved methods. And for that, the parameters included grain protein, flour protein, soluble prolamines, mixing development time, work input to peak, and work at peak. Those are the main measures of gluten strength. The MDT, peak, WIP, WAP, and also there's something called GSI, gluten strength index. Weather data, we collected weather data from nearby weather stations, and those data were aggregated from seeding to harvest, harvest 1 to harvest 2, and harvest 2 to harvest 3, and then harvest 3 to harvest 4. And then we analyzed the data using SAS, mixed procedure, as well as a package called the VCA in R. ANOVA was conducted to determine the proportion of variance contributed by each of the main effects, that was genotype, harvest date, location, and then their interactions as well. Genotype by harvest, location by genotype, location by harvest, and location by genotype by harvest. And then we did we used Tukey-Kramer method to determine statistical differences on the means. And graphs were produced with a package in R called ggplot2. So results. Here, I'm just trying to show the weather conditions, particularly during the harvest period. You can see that we got very high rainfall during harvest 2, the period between harvest 2 and harvest 3. Otherwise, during harvest 1 and harvest 1 and harvest 2, there was very little rainfall, but we had very good drying conditions here. The temperatures were very high. Between harvest 3 and harvest 4, again, there was very little rainfall, except for the site in Cross Isle, where we recorded about 56.4 millimeters. So this slide here shows the grain quality. What I want you to realize is that when you look at graph 1, at harvest 1, you can see that the grade consists mainly of grade 1 and grade 2, and a little bit of grade 3. There is really nothing in terms of what is called the feed, which you can call it grade 4 or whatever, but it's actually called feed grade. But if you look now at harvest 3, you start seeing the feed grade, which means the grades deteriorated with delayed harvest. Harvest 1, there were no feed grades, like I've said, and then harvest 3 and harvest 4, number 1, and harvest 4, there was actually no grade 1. All the grade 1 samples were gone. So what was the main thing that was causing that? The grain deterioration, mainly it was FDK, Fusarium damaged kernels. And this slide here shows the fact that with delayed harvest, there was an increase in the percentage of the Fusarium damaged kernels. This is shown at all the sites here. Just like you can see, this is a site in Brandon, a site in Cross Isle, and this is Carberry. If you look at Kelburn, we only have three harvest dates, because what happened is when we went for the 4th harvest, the geese had devoured everything that was there. This is the ANOVA results. I'm just trying to show you the main factor, the harvest date, because that was what we were very much interested in. And we can see that harvest date was significant in almost all of them. However, the contribution to the variance was very small, except for test weight. So harvest date had significant effect on FDK and test weight. And also harvest date contributed the largest amount of total variance to TW. So in this, I just want to show that sometimes highly significant does not necessarily mean a large contribution to variance. So this shows the mean separation for FDK. You can see here that FDK generally increased with delayed harvest. If you look at harvest 1, it was 0.341, and then in harvest 3, it was 0.488, and it showed that there was a significant difference. This is the 1,000 test weight, and you can see again that the test weight in both test weight and flower ash decreased with delayed harvest. The good thing is that the TW didn't go down below 75 kilograms of per hectoliter, which is required for your samples or your grain to be graded as grade number 1. And then this results here just showed the MDT, WIP and WAP, and the GSI, which I told you are very important when it comes to determining gluten strength. And again, we can see that here, harvest date had a significant effect on all of the gluten strength parameters, but it contributed very little to the total variance, about 0.6 to 0.39%. So this is the mean separation. What you can see here is shows that all these parameters generally increased with delayed harvest, which if these things are increasing, this means it's a good thing. I mean, if they are increasing, you want high MTT and higher WIP and WAP, and also the GSI. This graph here just shows that on top here is the WAP at Brandon, Carberry, Glen, and Harvest. And you can see that generally it increased with delayed harvest. Same thing here with the WIP. It generally increased with delayed harvest. Same thing for I'm showing here the site, and also here I'm showing the genotype as well. Sorry, I'm showing the genotype for WIP and also the genotype for WAP. And then this shows the MDT as well. It's again, generally it increased with delayed harvest. And again, it shows the GSI also generally increased with delayed harvest. And for all, I want to say for all the genotypes, you can see that there is a general increase in GSI and MDT. So in summary, what we have seen is that delayed harvest negatively impacted wheat grade. And the main degrading factor was Fusarium damaged kernels. So which means that it is important to harvest as soon as practical after physiological maturity to limit the grade degradation and economic loss. And what we have seen is most wheat quality parameters were not negatively affected by the delayed harvest. However, test weight and flour ash were reduced. And surprisingly, the gluten strength parameters marginally increased, which means it became stronger due to delayed harvest. I'm saying here it's gracefully aging like wine. I would recommend that we need a longer duration study because this one was just 1 year. And I would like to acknowledge the funders and where we got the weather data. And if you are interested, this paper has been submitted. It's in review. And also, like I said, this was a bigger study. We have already published one study, which was looking at the influence of weather on gluten strength. So if you're interested, you can go and read that. It's in the Journal of Cereal Science. Thank you very much.
Thank you very much, Manasa, for that presentation. I'll just remind everyone, if you have any question, we have a few minutes for questions. Feel free to post it in the chat. And I see a question here already from Ashton. There seems to be a trend towards gluten-free products on health grounds. Have you come across wheat varieties that are low in gluten and get towards this emerging demand?
I really don't know. I know that the varieties that we were using were chosen because they had different gluten strength. They differed in their, I would say they differed in their strength, gluten strength, going from the highest to the lowest. So, but I don't know. I mean, yes, genotype has an effect on gluten strength.
Okay, great, thank you. Any other question? Just wait for a minute. And I don't know if it's something that you looked at in your study, but looking at the variability in weather as we are seeing right now, and I think would see more of it into the future, what are the impact of a changing climate to the study in terms of looking at gluten strength in relation to delayed harvest?
Yeah, I guess, I mean, it's going to impact, particularly if we get situations whereby towards the end of the season we get snow and maybe we get too much rain, such that producers cannot go in and harvest because it's going to affect the quality of the grain. Yeah.
Okay, that's great. Well, thank you so much for that. We have just a couple of minutes before the next presenter. So I would still kind of just open it for any discussion. I think we still have Dr. Bullock here as well, if anyone has questions that we weren't able to address when Dr. Bullock gave his presentation. Because I know some people may want to join from other sessions, so we have to wait until 8 right on time before we have the next speaker.
What was it? I was allocated more time than, was that so?
Yeah, we could have also had a 5-minute break in between.
Okay.
But
Okay.
but yeah, no, well, it's coming up to.
Yeah, I have a question for Dr. Bullock.
Okay. Well,
Yeah,
maybe make it really
yeah,
quick.
yeah. I just wanted to find out. I mean, when you was showing the CVs for the yields, the CV for Manitoba seems to be. It's not that. It seems to be stable.
It's more stable. I
Yeah.
know standard deviation is going up at around the same rate that the mean yields are increasing.
Mhm.
And it may simply be that Manitoba in some of those really severe droughts sometimes does not get as severely as affected. Now, 2021 was an exception to that, obviously, because some of the worst drought affected areas were in the Interlake and central regions, eastern regions of Manitoba, but that was 1 year only. But yes, that is correct. I mean, you're seeing variability increase, but it seems to be going up at about the same rate as the mean yield is increasing because the CVs are fairly stable, more so in Manitoba than other provinces. And that could be the reason why.
Okay, great. Well, thank you so much for that. We would move on to our next presenter, Tarai Matengu, and he would be presenting on developing Fusarium and Blight risk models for Western Canadian cereal using weather data and logistic regression.
Okay, thank you very much, Timmy. Can you see my slides?
Yes.
Okay, thank you. Yeah, so I'm Tarai Matengu, and I'm a graduate student at the University of Manitoba Soil Science Department, and I'm working with Dr. Poplo and Dr. Mkabila on this project, which is titled Developing Fusarium Head Blight Risk Models for Western Canadian Cereals using Weather Data and Logistic Regression Models. So Fusarium Head Blight, or FHB, is a disease that infects small cereal crops such as wheat and barley during flowering or anthesis. That is when you see those anthers shooting out of the wheat heads, causing bleaching or spikelets in warm and humid conditions. So the pathogen reduces grain filling in infected heads, causing shriveled and lightweight kernels, which reduces the milling and baking quality of flour. And FDK in barley also causes pear gushing. As a result, barley samples with more than 0.2% FDK are downgraded from #1 grade. So the main concern with FHB is that it produces mycotoxins, particularly deoxynivalenol or DON, which is toxic to humans and livestock, especially pigs and lactating ruminants. So several buyers reject samples with DON levels that are greater than 1 parts per million. So one of the management options to help reduce the potential severity of FHB is to grow varieties with higher levels of FHB resistance. So under conditions with high FHB pressure, a variety with higher level of resistance should experience more limited impact from the diseasing. So fungicide application around anthesis also plays a major role to reduce FHB infection. However, the occurrence of FHB is sporadic, and fungicide application in years of low disease pressure can be costly. So one of the ways to decide whether fungicide application to control FHB is worthwhile is to forecast FHB occurrence based on weather conditions. So each province in Western Canada currently has these types of FHB risk maps available. But however, there are two main challenges. So firstly, the models behind these maps were developed many years ago and may not fit the current FHB chemotypes, which have been reported to shift from 15A DON to 3A DON, which is more toxic. And secondly, these maps use different models and risk levels, which is of concern, especially to producers near the provincial borders. For example, when FHB model focus high risk in Saskatchewan, but low risk near Manitoba border. Therefore, the main objective of this project is to develop and validate weather-based models to forecast the risk of FHB epidemics in wheat and barley in Western Canada. So this project has three main components. So we are working with the agriculture departments in all three provinces to collect data in the plot study for model development. which is the first component of the project, and from the producer fields for model validation in the second component. And the third component is the development of an online viewer that provides access to producers anywhere in Western Canada, and that will make use of the weather networks on the prairie to calculate FHB risk. So for the plot sites, which is the first component, we conducted field experiments in Manitoba, Saskatchewan, and Alberta in 2019 and 2020 at 15 different plot sites. And our plot sites were spread out geographically to experience different weather conditions and FHB occurrence in Western Canada. And we conducted separate experiments for each of the crop types, and crop types included winter wheat, spring wheat, barley, and durum. And these were planted in a randomized complete block design. And treatment were the 3 FHB resistant categories. For example, in barley, were the moderately susceptible variety, intermediate, and moderately resistant variety. And as all durum varieties are susceptible, only one variety was grown as shown in this picture. And the response parameters which we measured included FHB index, FDK, and DON. And these response variables were then classified into 2 classes of epidemic and non-epidemic cases using different thresholds. For example, the FHB index utilized 10 and 5% threshold in all crop types. And the 10% FHB threshold is the one utilized in the US FHB modeling. And the FDK threshold differed according to crop type. For example, spring wheat uses 0.3% FDK threshold. And this FDK threshold reflects to the maximum level permitted in the number 1 grade for each crop type under the Canadian regulation. And this serves as the justification for application of fungicides to avoid revenue loss due to downgrading. And DON threshold correspond to a value that results in wheat toxicity and refusal by some buyers during marketing, as established by the Canadian Food Inspection Agency. So to determine if weather conditions were favorable for FHB infection, we installed a weather station within 10 meters of each site, as shown here, and weather stations collected weather data on an hourly basis, including wind speed and direction, solar radiation, rainfall, temperature, and relative humidity. And these weather stations were calibrated to ensure that they were recording similar measurements before their deployment. So to develop logistic regression models, the weather variables were then treated as predictor variables, and we calculated 8 weather predictor variables from 5 durations around flowering. That is 4, 7, 10, and 14 days before mid-anthesis, plus a period between 3 days before and 3 days after mid-anthesis. And these variables were obtained from, firstly, the calculation of mean daily values, for example, mean daily rainfall. And secondly, from the duration in hours of a pre-specified condition. For example, the duration in hours where air temperature is between 15 and 30 degrees Celsius. And thirdly, from a combination variable, for example, the duration in hours where the temperature is between 15 and 30 degrees and where relative humidity is greater or equal to 90%. So Kenda correlation and stepwise logistic regression procedure were then used to identify variables mostly related to FHB disease. So logistic regression models were then developed using only selected variables using prog logistic in SAS. And model evaluation and selection were based on several factors, including area under the curve, Uden index, and Hosmer and Limshaw fit test. So moving on to results. So to develop valid FHB logistic regression models, the dataset should contain at least 25% of either epidemic or non-epidemic cases. And this table here shows the percentage of FHB index, FDK, and DON epidemic samples after binary categorization. And only models with highlighted disease indicator threshold were developed. For example, only Durham Dawn model with 1 milligram per kg were developed. That's the Dawn models with other crop types could not be developed since they had less than 25% of epidemic cases. And the best 2 selected models per each crop type and disease indicator are summarized in this table. And what is important to note on this table is that the accuracy of this table of these models was 74% or greater. And the model with the lowest accuracy was winter wheat FHB1, highlighted in red, which had an accuracy of 74%. And the model with highest accuracy was spring wheat FTK1, highlighted in blue, which had an accuracy of 85%. And another important thing to note on this table is that relative humidity was a frequently selected weather variable in these models. For example, all FDK and Dawn models uses only relative humidity to predict FHB risk levels. So although these models have greater prediction accuracy, they need to be tested or validated using an independent data set. And we did so from using data from processor fields that we collected in 2019 and 2020. And the selected processor fields were geographically distributed across Western Canada to maximize the expected variation in weather conditions and disease occurrence. And weather data was sourced from over 500 provincially and federally monitored weather stations, and the GPS coordinates associated with each processor field were used to identify the closest weather station with hourly and daily weather data. And this weather data was then used to calculate the predictor variables of the selected models. And the performance of FHB index, FDK, and Dawn models in the validation dataset is summarized in this table. And the accuracy of these models ranged between 66% for the model highlighted in red and 100% for those highlighted in green. And only the models with high accuracy in the validation dataset were selected for final use. And you can also note that our sensitivity for most models was low or infinite due to lack of epidemic cases. So the final selected models were then used to power an online FHB viewer. And the picture in this slide shows the homepage of an online viewer currently under development for use on either a web page or a smartphone. And the map is the most important section for the viewer. So users will be able to select an assessment date, the crop type, variety, and risk category to generate a map showing low, moderate, high, and very high risk. And the last section of an online viewer is the frequently asked questions, and it will provide further information on the map and the accuracy of the models. And in closing, this project was made possible by funding provided by a consortium of partners under the Integrated Crop Agronomy Cluster, and we greatly acknowledge their support. Thank you.
Oh, thank you very much, Tarai, for that presentation, and would open it up for questions. And good job on the timing as well. Got some time for questions.
Yeah, I just asked a question from here. My typing is very slow.
Yeah.
Do you like I heard there's like install 2 climate stations, weather stations near each other, like 10 meters. Do you find any difference in the weather variables between those 2 stations?
Okay, so the weather stations that I showed in the slide, it was from Kelvin. So we had extra weather stations. So it's just to install 2 weather stations, but we ended up not using one of the stations because it stopped during the growing season. Otherwise, we could have compared the 2 weather stations. But however, we noticed that if you from the plot sides, the weather stations were near the plot sides. But however, for producer fields, the distance between the producer field and the weather stations were different. And what we noticed is that, so if the distance between the weather station and the producer field increase, it reduces the model accuracy, especially with models that uses relative humidity. which is expected because it might be difficult to extrapolate relative humidity data. But for those models that use temperature data, they were more stable. But it should be noted that the accuracy of these models were still above 74%.
Thank you.
Great, thank you very much for that. There's a quick question. Did you have any yield loss numbers due to Fusarium under low, medium, and high epidemics?
Okay, so we didn't measure yield loss in this project. So what we're basically doing is to collect at least 1 kilogram per each replication, and from that grain we then use to calculate FHB index, to calculate FDK and DON. So we didn't do any yield loss in this project.
Okay, great, thank you. And I'm sure you can follow up with Ashton for further details about that as well. Thank you for your presentation. We'll move over to Dr. Champagne Catherine, and she'll be presenting on feeding models for food production. So scaling meteorological and biophysical data sets for agroecosystem modeling. Take it away, Catherine.
Great, thanks. You can hear me okay?
Yes, we can.
Okay. Hi, everyone. I'm Catherine Champagne. I'm with the National Agroclimate Information Service at Agriculture and Agri-Food Canada, and I'm going to talk to you a little bit about some of the weather data sets that we've been working on and evaluating for use in model scaling. Okay, so many crop models, many agro-ecosystem models are being looked at as tools for scaling up experimental results to come to broader understanding or broader conclusions about the impacts of things like best management practices on the environment. And many of these models have been run and calibrated against stations that are located either within or adjacent to the field, and are usually used with very good meteorological data. But if we want to scale up these models to look at, instead of just a single field, to look at a much larger area, we need data sets that match the effective spatial scale of the processes that we're trying to look at. So the purpose of this work is to evaluate how existing gridded model data sets can be used to optimize model implementation over broader spatial scales. What can we measure, what can we model, and what are the trade-offs in terms of using these in process-based models. So I was very happy to see in Public's talk some lovely maps from our team at Agriculture Canada. We maintain a database of climate stations for agroclimate mapping, for agroclimate modeling. We don't collect a lot of this data ourselves, but we harvest it from many other organizations and do a daily quality assurance, quality control of temperature and precipitation data sets. We've been doing this since 2006. And it's coupled with a gap filling system that goes back to 1961 for running a series of agroecosystem empirical and indicator models for assessing agroclimate risk. So this is a map showing the distribution of the stations across Canada. The red line is the agricultural regions of Canada, and you can see that there's a very uneven distribution of these stations in space, especially when you get outside of the agricultural extent. And we currently using about 2,500 climate stations on any given day. About a little under half of these are from Environment Climate Change Canada. Some are from the Coco Ross Volunteer Network, many from provincial networks, so Alberta Environment, Manitoba Agriculture and Food, the Quebec Mesonet, and the New Brunswick Department of Natural Resources. And we also use the Doppler radar network. We don't use that measurements directly, but we use those to help quality control the data set as it's evaluated. So the issues with the uneven distribution of these stations in space and time means we need to start looking at some other data sets to fill in the gaps where we don't have measured data. So we've been looking for the last few years at numerical weather data, near-term forecast data, analysis and reanalysis data from Environment Canada. And we've been primarily looking at four different data sets. So the 10-kilometer regional deterministic prediction system, or RDPS, and that's coupled with the regional deterministic precipitation analysis, or CAPA as it's commonly known. And we look at a similar model at a 2.5 kilometer spatial resolution scale, which is the high resolution deterministic prediction system and the high resolution deterministic precipitation analysis. So these are two data sets that meet our criteria for data needs, and that we can get them in real time. And they have broad spatial coverage of Canada. So these are two accumulated precipitation maps. The top one is the 10-kilometer and the bottom one is the 2.5 kilometer. And you can see when you zoom in that you can get some different levels of detail with those two data sets. How are these produced? These are from initial conditions and near-term forecast data from the numerical weather prediction system at Environment Canada, which uses the global environmental multi-scale model. And it's coupled with a land surface prediction system. And the CAPA product is an optimal estimate of precipitation using deterministic models, incorporating both in situ gauges and Doppler radar estimates. So we did some fairly extensive analysis of the CAPA product for use in agricultural applications. We looked at both daily and accumulated data sets over about a 10-year period. The assessment of the daily data showed a summertime bias of on average about plus or minus 5 millimeters. This map here is showing some of the variability ranging from sort of 40 millimeters with these sort of purple and red dots on either end of the bias spectrum. And you can see that generally in the middle of the country, we're getting fairly decent estimates, but depending on where you are, the biases can be much higher. And then we looked at those seasonally as well. So we're getting fairly good correlation with station-based data between our CAPA product and the measurements. We're getting correlations of about 0.7, and you can see that variability is much higher during certain seasons, particularly in the spring. So when we start to look at accumulated products, we looked at 2 years, and these are weekly, monthly, and growing season accumulation. So you can see when you look at weekly accumulated precipitation, we're getting a lot of scatter and some fairly high biases in some years, but not others. And those biases are generally reduced the longer the accumulation period, which makes logical sense that as you accumulate over a longer period, the impact of some off measurements becomes less. Again, it's also spatially variable. As this map shows, the darker colored dots are areas with higher residuals between the measured and model data. And you can see in areas with high precipitation, those biases are higher. And you can see in mountainous areas as well that you're getting higher biases. So we also wanted to look down at our field scale to see how we would incorporate this into our models. So for this, we were looking at our research farm in Ottawa, Ontario, the Canadian Food Inspection Agency farm. And for that, we used an in situ meteorological data station, as well as some field measurements of leaf area index. So the field site's equipped with a weather station that has incoming solar radiation, wind speed, air temperature, air humidity, and rainfall measurements. We also collected LAI 2200 measurements over a series of dates in 2018 and over a series of fields with different crop types. We also had soil moisture probes buried using time domain reflectrometry, and we used the 5 centimeter depth to validate some of our satellite data products. So we just started looking at some of this data for different years and for different periods, but in terms of the gridded temperature data sets, our minimum temperature data sets are showing a slightly higher bias than our maximum temperature data sets. So this is the minimum on this side, and then this is the maximum on the other side. And these golden points are the model data, and the blue ones are the weather station data. So we're getting a little bit more bias in the minimum temperatures. That seems to be having effect on the accumulation or growing degree days or crop heat units when these are calculated from these data sets. We're still investigating some of that data. And as you can see, that we have some gaps in the data set in the model data set. A lot of these are because of difficulties in getting these forecast data in real time. And also we experience some issues sometimes with time zone corrections. So time zones are somewhat artificial. And when you use a model product, the model is run at set times. So it's not calibrated for particular time zones. So the model right now produces every 6-hour data. So we've been correcting that with time zone shifting, but we can only do that within a 6-hour range. Some other key gridded meteorological data sets we've been looking at, solar radiation data. So that data set we're actually using the 24-hour forecast of solar radiation. And with that product, again, we're getting a slightly higher values from the model that we're getting from the measured, but decent correlation and relatively low bias. When we get at wind speed, we're getting much higher biases and a lot lower correlation, especially at high wind speeds, with our modeled product showing a lot more variability in the wind speed and a lot higher, a lot of overestimation, particularly at high values. And you can see that in the time series here on the bottom. And finally, the relative humidity, we only had a very short period to look at this data. We're going to look at this over a longer period, but as you can see, we're getting a lot of scatter in that data set with fairly low correlation. And as you can see from the time series, that we're getting much higher fluctuations than we're getting with our measured values. Some Earth observation data sets that can also support model optimization. So for this, we're looking at 2 data sets. We're looking at leaf area index from the Sentinel-2 satellite data, and we're looking at surface soil moisture. This is a commercial product actually from Vandersat. That's a combination of the soil moisture active passive mission and Sentinel-1 SAR data. Used as a downscaling method. So this is a sample of the leaf area index that we're getting from Sentinel-2 over our field sites. You get a lot of good delineation of different features that you can see in the fields. We also looked at several retrieval methods for getting LAI from the data, including using index-based methods, the Sentinel tool, Sentu Agri toolbox or Snap toolbox, and the Leaf toolbox in Google Earth Engine. And some of this work is, some of these data sets can be used to optimize unknown variables in the model. So things that we've been looking at are using the vegetation data for optimizing seeding date density, and the soil properties for looking at soil texture and soil moisture. So in terms of the leaf area index data, we're getting fairly similar results with the different retrieval models that we're using, with the Sentu Agri or the Snap toolbox giving us slightly better measurements than the index-based messages. And this is just a sample of some of the LAI time series that we were getting from cornfields in our research farm. This tool and scaling this up has become a lot easier. This tool's been translated now for the Google Earth Engine and the Leaf toolbox by Richard Fernandez at Canada Center for Remote Sensing. And I've given the link here if you'd like to go and try it out. It's quite easy to use. There's both a JavaScript version and a Python API version. And we're currently running a pilot to see if we can generate this for all of Canada on an on-demand basis. And just as a sample, we processed a fairly big chunk of Manitoba in a couple of hours. So it's a fairly big savings on data processing. In terms of the soil moisture, the current freely available soil moisture data sets from CMOS and SMAP weren't giving us the kind of information that we would need to support these types of field scale models. So we ended up getting doing some evaluation of a commercial product from Vandersat, which was recently purchased by Planet. And you can see this is for 2017, 18, 19, 20. So we're getting decently low RMSEs. We're getting good temporal trends, but the data is not perfect. So there's definitely some significant biases at certain times of year, which makes it a challenge to use it directly in these types of models. So we're still evaluating how we can optimally use this information, particularly in areas with high soil pedodiversity. And finally, we tried integrating some of these gridded products. We've so far just looked at the precipitation and temperature data in the sticks crop model. We use the high resolution product for that. And you can just see quickly the black line here is using weather station data. If we use just the gridded precipitation data, we're actually getting fairly similar results. But if we use the gridded precipitation and temperature, you can see we're getting a shift in that phenology that's coming out of the model. I think this is because of the overestimation of the minimum temperatures in the data, but that evaluation is ongoing over a larger number of sites. So to sum it up, scaling models from fields to regions is essential if we want to expand these over to a larger region of interest. But we need to understand what the biases are in these data sets if we want to use them effectively. The precipitation is showing pretty good spatial accuracy with some biases depending on where you are. But these are less impactful over long accumulation periods. The model temperature is also showing a good correspondence with the station data, but these small biases may impact the timing of crop phenology as it's estimated in the model. And finally, the satellite data sets are showing some promise, particularly the LAI data. And just one of the ongoing challenges is gap filling using gridded data sets. If you have any kind of gaps in the data, it's more difficult to fill these data sets than it is with using just a single station. So that is all for me.
Thank you very much for that presentation. Really great information. We don't have a lot of time for questions, so I would move on to the next speaker, but please watch the chat. Oh, I see Philippa sent a question on the chat, so please, Catherine, you can respond directly in the chat. Thank you very much. So we'll move on to the last speaker for this first session, Yunso, and Yunso will be speaking on crop yield forecast. Take it over.
Can you hear me clearly?
Yes, we can both hear and see your screen. Okay.
That's great. Yeah, I'm Yingshi Zhang, and also from the same National Agroclimate Information Service of Agriculture and Agri-Food Canada. I'm going to talk about the crop yield. Let me just get my point here. Explore the crop yield forecasting skills in climate extreme years by alternative treatment of technology-induced yield trend in Canadian prairies. So this is a very large group of people work on this, include colleagues from Agriculture and Agri-Food Canada, and also we have colleagues from Statistics Canada. So currently we have a model called Canadian Crop Yield Forecaster, which is an operational model. During the growing season, we use it both at AFC and Statistics Canada to generate some yield and production reports. Right now it's monthly, and sometimes we doing joint release with Statistics Canada. That's been in semi-public operation since 2013-14 in Agriculture and Agri-Food Canada, and also adopted by Statistics Canada in 2016, actually replaced the September survey. One of the model is generally performs reasonably well in the years with normal and close to normal climate but tends to overestimate the yield in climate extreme years. And especially last year, we find this problem is very severe, and we actually, by the end of the season, with the September forecast, we used the alternative algorithm, which made the model forecast and get very good results. This is basically the background of this study, and also the objectives, that is identify the causes of yield overestimation in years with climate extremes, and also explores alternative algorithm modifiers that might be improve the model performance in those years with climate extremes, and also explore environmental variables that could be used to identify the years with climate extremes. I think I got a lot of insight from Dr. Bullock's talk in this talk as well. And for this work, we start with spring wheat and canola in the 3 prairie provinces. I will show you the map. Is where our study is basically the 3 provinces, and include a little bit of the Peace River in the BC. That's and the green is where mostly the crops grow. Oh, sorry. And the dots are the climate station we used in this study, which is QA/QC with the process Catherine just described. And our modeling unit is by census agriculture region, which is reported by Statistics Canada. Yeah, I won't get into details of the model itself. It's use NDVI and climate variables and go through a versatile soil moisture budget model and get the crop related indices and doing the car level average, and also the temporarily we average by month or 3-week average and get the input into the table and into a statistical model to do the forecast. The statistical model is also we use. There's 3 major parts of this. One is just like Dr. Paul Bullock, so it's a very strong yield trade in most of the regions. So this have to be considered. And also there's a linear effect of all the predictors we've been like, such as water stress index, NDVI, frost days, heat stress days. There's many of those we have to put into a, we call robust regression model. And the predictors will be automatically selected, and the cross-validation process will limit the model for the predictor to make it not overfit the model. So I will show some results with the leave 1 year out cross-validation for spring wheat canola in the 3 prairie provinces. You see generally the model is following the trend and some variations very well. But some years which already been identified by Dr. Bullock, it's like 2021, you see the model is overestimated a lot, and 2001 to 2002, and 1988, this is for spring wheat. For canola, there's more years been like overestimate. There's 2021 definitely, and 2001 and 22, and also 2012, also a year, which is quite largely overestimated by the model. So in this case, we have to identify what is the problem for those years. How can we like do some modification to the model to make it better? So this is we analysis the yield trend in those, like you see in most of the cases, the yield have a strong trend, like the R square can be up to close to 0.8% in some regions. But it's very interesting. It's in those very dry areas with very frequent drought in those regions, southwest Saskatchewan and for canola and southeast Alberta. There's not much trade found. It means the technology or the input doesn't do much. So that's give us some idea. Maybe in those years with extreme dry condition or drought condition, there's something like with the yield trend in the model may not fully realized in those years. Like you put more fertilizer in it, in the dry year, it doesn't do much. So the trend which is supposed to happen, not happening. So that's the assumption behind this the modifications study. It's just a first attempt. We just try to identify the extreme years with some index. Currently, I just tried the stress index, which is 1 minus actual evapotranspiration over the potential evapotranspiration. We call it stress index, and also we use the total precipitation from May to July. So this is just a first attempt to try to attempt. It's give me some results to can identify some years. You see, like the 2021, it really gives you very big low precipitation, also very high stress index. This is for canola, and this is just for one car, but I analyzed all the cars in the Prairie provinces. It's have the very similar trade, but sometimes it doesn't work with these two index. So the first attempt, we try to reduce the certain years of the trend. We cannot reduce all of them because you see that in the later years, the trend anyway, it's higher. So we just have a modifier associated with this stress index or the soil, like the precipitation, so that it can be identified. It's basically we use the 0 to 1 modifier, depends on the extreme condition. It's currently just linear. We haven't explored. It's still some work in the progress. So this is our first try. So the top is adjusted by the departure of the total precipitation from May to July, which to their mean, which is I use a standard deviation 1 and 2 standard deviation. It's going how it can be affect the 0 to 1 modifier. So this is for spring wheat, for the canola. You see the canola for last year 2021, it's worked very well, but some other years it's although have some effect, but not really to the extent. For those like 1988 as well, it doesn't really pick up. And for spring wheat also has some effect, but not very successful. But especially for the 2022, we don't know. It's not a dry year. I'm not. Maybe there's some other effect like other Bullock the sowed that we need to identify. So for the bottom is with the stress index, it's very similar, a bit better, I would say, for some years like here. But in January, we had some success, but still it's a work in progress. So I think I'm going to summarize this. So current operational yield forecasting model tends to overestimate crop yield in years with climate extremes. There is a need to calibrate the forecasted yield in those years. And an increase in yield trend by technology advancement with year explained about 10 to 70% of the historical spring wheat and canola yield variation in Canadian prairies. The crop region without significant year trend are located mostly in the drought-prone region. So that's the expected trade yield might be limited by the extreme conditions such as severe drought. That might be a contributing factor in overestimated crop yield in extreme years. Some improvements in forecasting scales are achieved by adjusting forecast yield using 2 extreme climate indices. One is the total precipitation from May to July, and another one is the stress index. However, the scale improvement is not demonstrated in all cars or in all the extreme years for the 2 tested crops. So future work will include continued search for more representative extreme indices for different crops in different regions, might be even combined indices for those different kind of limitations. Also, maybe we look into other ways to improve forecast scale, such as the machine learning algorithm. I think I will conclude here. welcome for any questions.
Thank you very much, Ian. So I know that I'm one of the people that always look forward to your crop yield forecast. And yeah, so please, if you have any question, feel free to unmute and actually ask, or you can type it in the chat. Well, while we wait for a question, I think a question I have for you is, we've actually seen it happen in which, and I really like the fact that you are trying to use the deviation from normal to check the stress index. But we've actually seen, and Dr. Paul Bullock's presentation also shows that sometimes within the same growing season, or even within the same month, you go from one extreme to another, in which you have drought persisting until the last few days of the month, and you have 200 or 300% of normal precipitation occurring. So how do you account for the intra-temporal variability that you'd see within that month?
Yeah, I think that's a very good question. And also I noticed that from Dr. Bullock's talk, I think that's something we need to consider. Right now, I only use one single indices to identify those years. Looks like even 2 watt, we didn't say the 2 watt, we didn't even say that excluded in my exploration. But I think in the future, we may have some combination. If this happens in this period, this happened in that period, we can identify those, try to modify those, try to come up with some modifier, combine all those indices. I was even thinking about 1 year, it's the temperature actually had some effect.
Yeah.
So those are really something we need to explore.
Yeah, no, that's great. And Catherine said, it's a complex system. So we'll keep really just adding one thing, sometimes one at a time. Other times we need to maybe include multiple indices.
Yeah.
Okay,
another thing I was thinking about, because we do forecast from July, August, September, each month we update. So we have to find out at what point we can identify those, the either extreme effects. We can really see this is a year we need to do this. Otherwise, it's too early. Like last year, the first two forecasts we definitely overestimated, but the last forecast we did some modifier, it's bring it down. But can we do it early? That's something else we also need to explore.
Yeah. Great. Well, thank you very much. And this concludes this first aspect of the session on understanding past, present, and future effects of climate and agriculture. We want to appreciate you for joining the session. The next session, part 2, is actually starting in about 17 minutes or so. About 17 minutes thereabouts. Hopefully you'll be able to join in. We have interesting speakers lined up for that as well, 6 speakers for the next session starting in about 17 minutes. Thank you and see you then.
Are we going to be in the same room or we will have to different room?
I actually think it's a different room.
Okay, let's join again.
Sure. Yeah.
Okay.
Okay. Can I stop?
Yeah, recording, please. Yeah, you can stop the recording.
Okay.